Good morning, everybody. Can you hear me now?
Yes, we can.
Good morning. Can you hear me?
Yes.
Good morning, yes.
Can you hear me now?
Yes.
Hello? Okay. Good morning, everybody. Thank you very much. I think the connection is great today. I hope you had a great celebration week, Independence Day. Um, I wanted to start from the point where we stopped last time. First off, I would like to know, please, I need to know how many PTech students we have in the room, because I need to make a report every time. I was confusing last time. So, like I say, you can also text me if you don't want to tell me now, or if you have an issue of mic, you can text me or you can send me a chat. I hope everybody has my number in case for quick reply, I can provide you my number, but you have to use a WhatsApp or Viber. Okay, that makes things easier because I'm outside of the country. If you text, the roaming cost is too much, so it costs you, it costs me as well. Uh, the number that you can reach me on WhatsApp is 410-292-2110. Okay. Download WhatsApp on your phone. I believe it's called WhatsApp or Viber. Uh, they are free. Actually, whenever you want to call people outside of US, you can download these two application, and you can able to call or text people, and it doesn't cost you anything. As far as you have a good internet connection, you can reach your relatives. Uh, without paying any money. So you can text me on this number, or if you can tell me now, that would be wonderful. That will help me a lot because I just got confused last time. I know that some of you told me that you are in the PTech program. Can you share that to me right now, or you like to text me? What do you prefer? Or you can send a text message. You guys hear me, right? Hello, do you guys hear me?
Yeah.
Okay, Oti, thank you. So please let me know who is in the program of PTech. That's for my document, for my record. I would like to get the information because I need to submit your report, your academics reports. That's very important. So send me or you can email me. Okay, you can email me. That's also another option. Okay, either way, you can text me or you can email me. All right. So I wanted to wrap up chapter 9 today. I think we discussed so many things. Again, the PowerPoint presentation, the practice example, all of them are in the module section. So today, maybe I can go to the last part of chapter 9 because we are almost 2 weeks now. We need to wrap up this, and we're going to have our first exam on chapter 8 and chapter 9. Before that, I will send you the review guideline, what you need to know, what you need to prepare. So maybe Friday, today's Wednesday, Friday, we'll be working on the review guideline. I'll post that for you. So we're going to do some practice problems today regarding with that. But before that, if you have any questions that you want us to get explanation, you let me know. I think I was, let me see. We're discussing VACPR model. We're discussing a tetrahedral, and I think, let me see here. Okay, maybe. Okay, I may start maybe a little bit about, I don't know if I discuss about the bond dipole moments. The dipole moments are added together to give an overall molecular dipole moment for two triatomic molecules. Um, Let me see if for two triatomic molecules with different structures. First off, we were talking about the dipole moment in chapter 8. The dipole moment can be calculated as mu equals to charge times r. Okay, that is how we can able to calculate the dipole moment quantitatively. Okay, quantitatively. Um, So always last time we were talking about that if there is an unfair distribution of electron, there is always polarity. Okay, we were given example with hydrochloric acid, and we have seen that the huge number of electrons are on the chloride section. If you assume the red color is electrons, and then there is few electrons on the hydrogen part because there is a high tendency of electron negativity on the chlorine side, which we can represent as sigma minus, and there is a low tendency of attraction of electrons on the hydrogen side, which we represented as a sigma plus. So this actually, whenever there is unequal distribution of electron, that's called a polar bond. Okay, that's polarity. That's how polarization starts. But if you have, I think you need to mute your mic, Oti. I think I may have to mute you, Oti. Sometimes when we forget to mute your mics and there is a back noise and everybody will hear you, and we don't want to hear your personal matters or discussion with the other people. So mute yourself, please. Okay, if you have any question, raise your hand, and then I will try to accommodate you or at least give you the mic to ask questions. So let's go back here. That say, for example, you may have a chlorine molecule, right? This is a diatomic molecule. A diatomic molecule basically means that it's a molecule made from two atoms, right? It's a molecule made from two atoms. So we wanted to investigate about we wanted to investigate about with the polarity of the chlorine atom. So the bond that's formed by chlorine and chlorine is going to be a single bond. So they have the same they made from the same atom, okay? They are a diatomic molecule, so the distribution of electron is the same, okay? So this is going to be non-polar. There's no polarization here, okay? This is how polar and non-polar is about. Now, this is just by looking up the individual atoms, okay? By looking up the individual atoms, you can able to predict whether a molecule is polar and non-polar. Sometimes this is not the only way that you can able to identify or explain polarity of a molecule by looking up the geometry. Okay, remember that here in chapter 8 and chapter 9, we spend our time to discuss about the significance of the geometry of the molecule. So we have a geometrical structure here, carbon dioxide, for example. If you look carbon dioxide has a linear structure. This is CO2. So if someone will ask you, can CO2 would be a polar or a non-polar molecule? So it's very hard to answer this question. Okay. Don't just expect that because carbon dioxide is made from two different individual atoms, carbon and oxygen, right? You may have to jump to the answer, okay, there is an equal distribution of electron. There is an equal distribution of electron, and that means this leads us to polarization. This leads us to polarization. So that I think Uh, that I think is wrong, because when you look on carbon dioxide, you have to draw the geometry of the molecule. So when we draw here, you can see carbon at the center, okay, oxygen on the side, okay. So the bond dipole is uh, a vector quantity, as a vector quantity. How many of you somehow took physics? How many of you somehow took physics? Do you know the difference between vector and scalar? Vector means that it has magnitude and direction. So the vector quantity from let's consider here with carbon and oxygen, always the electron negativity goes from the lower electron negativity from carbon to oxygen. So if you have a periodic table, you can see that oxygen is on the right side of carbon. So oxygen has a higher electron negativity. So the arrow here shows you it goes to the right. Okay. Again, on the left, the from carbon, it goes to the left. Okay, so what this tells you that you have two vectors. The two vectors have the same magnitude. The magnitude is the same, but they have different directions. Okay, so maybe you have mu plus here, this is like from the right, this is mu minus here. So the summation of the vectors can be added. So if you can add u plus and u minus, it gives you 0. So that means there is no net dipole moment. There is no net dipole moment. So that means if there is no net dipole moment, carbon dioxide is nonpolar. So what I'm trying to say here is that polarity of a molecule determined also by the geometry of the molecule, the way how we draw. Last time we discussed about linear geometry, we discussed about trigonal planar geometry, tetrahedral geometry. We also discussed about octahedral geometry, etc., etc. So these are the type of geometries that we discussed. So that geometry also gives you whether the molecule is polar or non-polar. Okay, whether the molecule is polar or non-polar. So let me give you, for example, we have a situation here. Um, Let me just create a slide here. So if you consider carbon tetrachloride, okay, um, carbon tetrachloride, and someone wants to know that whether this is polar or non-polar, okay, as a molecule, okay, as a molecule, okay. Of course, here it's very important to know that there is a difference of electronegativity between carbon and chlorine. We know that carbon has low electronegativity. Carbon has low electronegativity uh, because carbon is on the left. Okay, carbon has low electronegativity. Okay, and chlorine is on the right. Chlorine has high electronegativity. I don't need to study this. I just can look on the periodic table. If you look on the periodic table, chlorine is in group 7 on the periodic table. Carbon is found in group 4. Okay, so any element which is on the left always have low electronegativity. So obviously between the individual atom, between carbon and chlorine, there is polarity. Okay, there's polarity. There's no question about it between the individual atoms. Okay, between the individual atoms, there is a difference of electronegativity. There's a shortage of electron here, which we represent by sigma plus. There is a huge amount of electron here represented by sigma minus. This is on the level of the individual atoms. However, we wanted to determine as a molecule, if carbon tetrachloride is a polar or non-polar. Okay, so to do that, we need to draw the structure. Okay, we have to put carbon and chlorine. There are 4 chlorines here. Okay, so in this case, the structure is pretty much tetrahedral. Okay, so if you consider this, the tetrahedral structure, there is always a vector, the dipole moment, which is the dipole moment. Dipole moment is mu, right? So there is attraction of electron from carbon to chlorine. There is attraction of electron from carbon to chlorine. There is attraction of electron from carbon to chlorine. There is a flowing of it. Instead of saying attraction, I would choose the word flowing of electron. So they are flowing in opposite directions, but the magnitude is the same because the attraction is the same. So if this is mu plus, this is going to be mu minus, this is a dipole moment. If this is mu minus, this is going to be mu plus. Mu is a Greek word. Mu is a Greek word for representing a dipole moment. Now, to determine the entire dipole of the molecule, we have to add up all of the vectors, all of the vectors. So they are in, as you see here, they are in opposite direction. They have the same magnitude, but in opposite direction. So how do I know? That's a question here. How do I know that they are in the same magnitude? The reason why, one way that you can tell that they have the same magnitude, because the attraction is between carbon and chlorine in every corner. In every corner, the attraction is between carbon and chlorine. So mu plus and mu minus will be zero. Okay, so that means the geometry of the molecule for carbon tetrachloride, the entire geometry of the molecule is going to be zero. That means it is non-polar. It is non-polar. Now the question is for, okay, well, let's change let's change the perspective in a little bit different. Instead of chlorine, say for example, I may have this kind of structure, CH3Cl. Okay, this is called a methyl chloride. Methyl chloride. Okay, now that means now we have like a structure. Okay, let me just clean this up a little bit. If I can able to clean this, it's not clean from my end. What's going on? Okay, here it's clean. Okay, wonderful. So we have CH3Cl, and if I want to draw the structure, I have carbon at the center. I will have hydrogen on the end. I have 3 hydrogen. Okay, and I have chlorine. Okay, so the attraction between carbon and hydrogen again is a vector quantity. Would go this way. The attraction between carbon and chlorine would go this way here. So the dipole moment of carbon and hydrogen would be mu plus, okay? But the dipole moment with carbon and chlorine would be mu minus, but the values are not the same because obviously the dipole moment of carbon and hydrogen, which is mu, is not equal to the dipole moment of carbon and chlorine, okay, which is also mu. The mu value, mu refers to Greek letter, which is dipole moment. That because dipole moment can be calculated as charge times R, okay? So you have to consider what would be the distance between carbon and hydrogen versus carbon and chlorine. They have a different charges. So we don't expect here mu plus and mu minus would give us zero. It's not equals to zero because as you see here that chlorine is different than hydrogen. So if this is not zero, then it's not non-polar. It's going to be what? It's going to be a polar. It's going to be polar molecule. Okay, because of the chlorine atom present here. If everything was like this, if everything was hydrogen, it's hydrogen and hydrogen and hydrogen and hydrogen, So everywhere we go, the distance are the same, the charges are the same. So that will not be an issue here. In this case, this is a non-polar as a molecule, but this one is a polar molecule. Okay, so my point here is that polarity depends also on the geometry of the molecule. Because polarity has to be dependent by the geometry of the molecule. So that's one of the significant parts of polarity. Okay, uh, so to determine to determine the polarity, you have to draw the geometry as well. If there is any question, I'll try to address your question. Okay, uh, so that's about polarity of the molecule. Let me go. Oh, we discussed about the valence bond theory last time. I think I spent time on the valence bond theory. I remember that. That's the difference between Lewis structure and the valence bond theory structure. The valence bond theory structure talks about um, bonds are created by overlapping of the atomic orbitals, right? We're talking about that. Okay, um, so we have different types of orbitals. We have like s orbital and p orbital. We have d orbitals. We have f orbitals. There are four major types of orbitals: s, p, d, and f. Okay, so now in the hybridization system, this is a good hybridization of a good example of hybridization of s and p orbitals. Say, for example, to form the overlapping of two orbitals s and p. Okay, mostly s and p orbitals can create a linear geometry, 180 degree. Okay, if one s and one p are involved, the orientation will be linear. So orientation will be linear. Okay, if it is linear, it's going to be 180 degree. Okay, so the what energies are associated here, it's the energy level of a pure s and a pure b orbitals. So one s and one p creates two sp hybrid orbitals. All right, two sp hybrid orbitals, and the angles associated with that is always 180 degree, which is a linear geometry. Okay, now let's break down this a little bit. Say, for example, if one s and two p's are involved in forming bond, I say px, py, two p's are involved because the s has only one orbital. The s subshell has one orbital from 101 class, if you remember. P has three orbitals. Okay, d has five different orbitals. Okay, f has seven orbitals. We're not going to talk more about F. We're going to focusing on the S, the P, and the D orbitals, because most of the geometry of the molecules will be formed by these three orbitals, by S or P or D. Okay, so if one S and two P orbitals are involved, uh, you will have one S and two P, you will have three sp2 hybrid orbitals. Three sp2 hybrid orbitals. So the three sp2 hybrid orbitals, because when we add them, 1s and 2p, it gives you three sp2 hybrid orbitals. So that the orientation of that orbital, the geometry will have a 120 degree. And a 120 degree, what type of structure would have a 120 degree? A 120 degree pretty much have uh, a trigonal planar geometry. So trigonal planar geometry is formed by one s orbital and two p's orbital. Remember, p has, like I say here, p has three orbitals, three different orbitals. Okay, so we'll have one s and two p orbitals, and we get 120 degree. Now, let's change the subject area a little bit different. So instead of one s, you have instead of two p orbitals, you may have three p orbitals. I'm coming to this case right here. Now, if you have um, one s and three p's are involved, px, py, and pz. There are three different orientation. P has three orbitals. So you will have 1s and 3p orbitals are formed. So the orientation would have a 109.5 degree. Do you remember what kind of geometry will have a 109.5 degree? What is the type of geometry that we're looking for if you get 109.5 approximately? It's going to be, can, can anyone tell me the 109.5? 109.5 is going to be tetrahedral, okay? Tetrahedral geometry. It's called tetrahedral. So you have four equivalent, because 3 plus 1 is 4, 3 p orbitals in one s orbital. So you have four sp3 orbitals. Okay, so that's going to be four sp3 orbitals. Four sp3 orbitals is corresponding with four sp3 orbitals corresponding with tetrahedral. Okay, tetrahedral. It's corresponding with tetrahedral structure. Okay, so in any case, this is okay. This is how the hybrid orbitals in the geometry of molecules are stated. Maybe we may have another example on the next slide here. I'm using this one here. We have if D is involved, okay, sp3d hybrid orbital. So now you have 1s, you have 3p, you have 1d, okay, a d orbital. So you have so that gives you 1s, 3p, and 1d. That gives you um, 5 sp3d orbitals. Okay, 5 sp3d orbitals, because 1 plus 3 is 4, 4 plus 1 is 5. There are 5 sp3 hybrid, I would say hybrid orbitals can be formed by overlapping 1s orbital, 3p orbitals, and 1d orbitals. So what kind of geometry, what kind of molecules are we looking, what kind of structure are we looking for sp3d hybrid orbitals? They're going to be a trigonal bipyramidal. Okay, a trigonal bipyramidal. So trigonal pyramidal geometry can be formed by overlapping, by including s orbital, p orbitals, and d orbitals. That's going to be trigonal bipyramidal. It has five, it has five corners, I would say. Okay. Now, the last one we have is that if you have 1s, 3p, and 2d orbitals are involved. Okay, 1s, 3p, and 2d orbitals are involved. What does that gives you? That gives you 6 equivalent hybrid orbitals that results when Ns, 3np, and 2n minus 1d orbitals are combined. 6 equivalent hybrid orbitals, that's 6 sp3 d square hybrid orbitals. So the type of geometry that corresponds with the formation of these orbitals with 1s, 3p, and 2d, the type of geometry that we will expect or we will get is going to be octahedral. Octahedral. Okay, so I'm going to make a summary how how what is the perspective point of view. What is the perspective of valence bond theory? Okay, valence bond theory. First of all, just to give you a summary, valence bond theory doesn't believe with electrons to form bonds. Valence bond theory stress that it's not the electrons, but it is overlapping of orbitals that will create bond. Okay, when they are talking about orbitals, they have s orbitals, they have p orbitals, they have d orbitals, they have f orbitals. Right now, we are kind of ignoring f orbitals. Okay, so to summarize this, we can able to say that. Let me just create a new slide here. If I create slide here, I can change the color maybe. If 1s and 1p orbitals are involved, we get 2sp hybrid orbitals. Okay, 2sp hybrid orbitals. That means the 2sp hybrid orbitals are corresponding with 180 degree. And 180 degree is associated with a linear geometry. This is going to be a linear geometry. Okay, if 1s and 2p's are involved, 2p orbitals are involved, then we get 3sp2 hybrid orbitals. Okay, so the angle orientation for 3sp2 hybrid orbitals is going to be 120 degree. 120 degree gives you a trigonal planar geometry. That gives you a trigonal planar geometry. And then this is like, I can put number 1 here, I can put number 2 here, and there are number 3, and I will have number 4, and I will have number 5 later on, depending on how many orbitals that I'm going to overlapping here that determine the orientation, at the same time that determine the angle of the molecule. So um, if I have 1s and 3p's are involved, say for example, I have px and py and pz, okay, I would have to get 1 plus 3p, 1s plus 3p, that gives me 4sp3 hybrid orbitals. 4sp3 hybrid orbitals. Now, 4sp3 hybrid orbitals are associated with the tetrahedral geometry, and the classical or the ideal tetrahedral geometry would be 109.5. The 109.5 is tetrahedral structure. Please take a note of this tetrahedral geometry. Okay, tetrahedral geometry. Okay, I'm giving the summary of the valence bond theory. Summary of the valence bond theory. I hope you can see this in the top. Valence bond theory. Okay, you guys can hear me, right? Am I on the mic? Because sometimes we have.
Yes, here.
Yeah.
Okay, thank you. Thank you very much. Okay. Okay. So let's continue with number 4. Number 4, now we consumed all the p orbitals because p has the maximum number of orbitals the p subshell can hold is 3. So now we come to a d orbitals. Okay. So let's say that we have 3 different orbitals, s, p, and d are involved. Okay, if we have a combination of these three, what kind of hybrid orbitals we get? That's the question. We get if one is all the three p's are involved. Okay, so one, two, three, four, three p. I'm sorry, and d one d orbital. So one, two, three, four, five. We get five sp3d hybrid orbitals we get. Because when we add them, five sp3d equivalent hybrid orbitals we get. Okay, so that actually the angle would be it's vertically we'll have 180 and horizontally we have a 90-degree angle. Okay, so we have like a vertical angle and we have a perpendicular angle of 90-degree. Okay, so that actually that kind of geometry is corresponding with a trigonal bipyramidal. Maybe I can give you some practical, after we've done this, we can do some practical questions and then it makes sense. It makes sense. We can able to predict that. A trigonal bipyramidal because we have five sp3d hybrid orbitals. The last one that we need to know here that let's say that instead of 1D, sometimes molecules need more than 1D orbitals. They consumed the S, they use all the P's, and they need another D orbital. So that means we have one S, we have px, we have py, three different orbitals, and we may have 2D instead of 1D. Okay, I can say dx plus dy because d has, first of all, d has five different orbitals. You can go up to five. Okay, p has three different orbitals, so I can just use xyz. S has only one orbital, so I cannot put one s x, one s x, one s y. If I put that on the exam, this is wrong. This is, I just want to trick you. Okay, s cannot have, s orbital has only one subshell, so s cannot be x, cannot be y. S has only one orbital. P has three orbitals. That's why I'm using x, y, z. I can use five different letters for d orbitals because d orbitals has five different I would say five different rooms to accommodate electrons. Okay, F has seven different room. I would say seven different spaces to accommodate electron. Okay, so when we add all this together, 1 plus 3 is 4 plus 2 is 6. We would have 6 sp3 d square hybrid orbitals. 6. Okay, 6, we can get 6 sp3d square hybrid orbital. So what kind of structure are we getting here? What kind of geometry we get in here? The geometry of the molecules that is formed from S, from 3p, and from D2 experimentally, that is octahedral structure. Octahedral structure. Oh, so we have to visualize this. We have to always when I ask you linear structure, according to the valence bond theory, linear structure can be formed by S and P, one S and one P. According to the valence bond theory, trigonal planar, which is a 120-degree, can be formed by two P's and one S. Okay, it goes like that, two P's and one A. So this is something that we have to, this can be help you to summarize, okay, the geometry of the molecules and then the overlapping theory. Okay, I hope you took notes on this. I will try to send you the video after the discussion. I will post this on um, I'll post this on YouTube later on, and then I'll send that to you, and you can also review that, the valence bond theory. Okay, so maybe let me move on here. Maybe the next picture might give us some hint or some idea about the overlapping of orbitals. hybrid orbitals involving d orbitals. That's going to show us, you see, you can see sp3d hybrid or hybrids, sp3d hybrids, that is ideal for, like I say, that's ideal for trigonal bipyramidal. Okay, you can see that from sp3d you can see that uh, one is three piece, one is px, the other is py, the other is pz. This is orientation, like one is on the x-axis, one is on the y-axis, and one is on the z-axis. And the 3D z, one of the z orbital also is involved. So altogether, they give you this kind of geometry, the geometrical structure. These are electron domains, actually, what we see here. So by combining all this P's and this S's and the D, you get sp3D hybrids. So the corresponding geometry would be a trigonal bipyramidal. The same you can see on the right, that there are orbitals involved. The involvement of orbitals here are s and p's. The three p's are here, all the p's, and one s and two d's, okay, are involved here. So they combined together, and finally they came up with this structure, which is sp3d square. And sp3d square, the electron domain looks like this. This is common in octahedral structure, in octahedral structure, okay? So that's how we explain the valence bond theory. Um, I just discussed about polarity already. We discussed about polarity earlier. So this might be a good example here about polarity. Earlier, I was talking about, I didn't provide you a quantitative number, but I'm theoretically explaining you that this is a molecule of HCl, for example. Here we have HCl. Whenever you have two atoms, the attraction, the dipole moment always goes from the attraction goes from the lowest electronegativity to the highest electronegativity, because this is chlorine and this is hydrogen. Okay, so obviously you can see that this is a polar molecule. There's no question about it. The geometry of the molecule even can tell you. But when we come to here, we have a molecule of carbon tetrachloride. Okay, so when we draw the geometry of the molecule, the attraction from carbon to chlorine is the same in every direction. So when we add this up together, it's going to be non-polar, because they have the same magnitude, but opposite direction. Same magnitude and opposite direction gives you non-polarity. Okay. Um, here is a good example of polarity, because of, if everything was carbon, the gray color refers to carbon. This is carbon, this is carbon, but this is chlorine here, because the attraction of carbon to chlorine is different, different than the attraction of carbon to chlorine here, and different than the attraction of uh, carbon to hydrogen. Oh, by the way, I'm sorry. This is hydrogen. This is hydrogen. The gray color refers to hydrogen. Okay, the black part is carbon. So we have the attraction of carbon to chlorine versus carbon to hydrogen. Okay, is different. So that when we add up, you don't get zero. It's not zero. So that actually creates polarity. Bromine trifluoride would be a non-polar, because it's the same molecules in different orientation. So geometry is one way that you can able to determine the polarity of a molecule. The polarity of a molecule. Okay. Um, okay. We discussed this too. I don't want to go back again. Um, how to create hybrid orbitals. So I wanted to, excuse me again, go back with, I wanted to give you maybe, okay, this is actually, this is, okay, this is important. We need to know about this. Is about the, when, okay, we talked about still we are talking about valence bond theory, right? So valence bond theory again, it's always working with overlapping. Okay, overlapping of what? Overlapping of orbitals. So how do orbitals overlap? That's another question. How do they overlap? So there are two ways. Okay, orbitals can overlap to form bonds between atoms. Two ways. Okay, what are those two ways of overlapping? Okay, what are those two ways of overlapping? Okay, so when we talk about that, we have to see those two ways of overlapping. Okay, um, okay. So let's see. Here are the two ways. Okay, okay. So one is a sigma bond. Please take attention because it's very important. The other is a pi bond. Okay. Now, sigma bonds are characterized by a head-to-head overlap, okay? So you have, this is the horizontal axis. This is a sigma bond actually is here. You have two p's, okay? The p has such a shape, this is a p has such shapes, okay? Such orientation, the electron density, p can be like this, or p can be like this, or this, say for example, this can be px, this can be pz, or p can be vertically, it can be py, okay? So the overlapping of the two orbitals, these are the orbitals of p, okay? The way how they overlap, if they are overlapping head to head, okay? This is like px, this might be another py. If they are overlapping head to head, then that's called a sigma bond. They have head-to-head overlap. They have a cylindrical symmetry of electron density. This is the electron density about the internuclear axis. Okay, the internuclear axis, first of all, is assumed to be. Let me add Marvelous here first. Okay, the internuclear axis is assumed to be the place where internuclear axis is a place where high high electron density, okay, high electron density is found. Okay, the place where high electron density is found, that's called the internuclear axis. The pi bond, okay, so sigma bond, by the way, this is very important, please. I'm going to ask you this on the question. Sigma bond is always stronger than pi bond. Pi bond is this guy here. Pi bond is the attraction. See, at the internuclear axis, you don't have any attraction. They have attraction at the top and at the bottom. It's maybe I can able to draw better picture here. If you have two p orbitals, okay, this is the middle one is the internuclear axis, but instead of communicating with the center, this is the internuclear axis. Okay, this is the internuclear axis right here at the center, internuclear axis. They have a connection above. Maybe I can use a different color here at the top, or they may have a connection at the bottom. Okay, the connection not necessarily be always at the center. So in that regard, if the connection is above the internuclear axis or below the internuclear axis, then it's called a pi bond. Now, a pi bond is weaker. Okay, a pi bond is weaker than a sigma bond. Why? Why is a pi bond? Pi bond is weaker. Okay, pi bond is weaker than a sigma bond. Can anyone tell me the reason? Why is pi bond is weaker? Because the reason why in pi bond there is a deficiency of electrons, or electron density. I would say a deficiency of electron density. You don't have too much electrons on the top or on the bottom. The electron density is much higher on the internuclear axis. Because we have to know that. Okay, we have to know the difference between a sigma bond and a pi bond. I'm pretty much sure the next slide might explain us with sigma bond and pi bond. It can provide us more example. So okay, so maybe like I can go to the next one here. Maybe we can let me see if we have example of okay pi bond. Okay, so there is a pi bond. Okay, we discussed about sigma bond. Like I told you, sigma bond is the overlapping of end to end. Okay, so this is sigma bond right here. A pi bond is a side to side overlap. Okay, so not on the internuclear axis, but on side to side. I don't like this picture. I think maybe they have to draw it this way here. A side to side means that okay, here or here. Okay, here on the center, that is the sigma bond. Okay, these are the pi bond here. These are the pi bond here, where there is a low electron density. So, it really gives you a good definition here. The pi bonds are characterized by the electron density above and below the internuclear axis. That's what I'm talking about right here, above and below the internuclear axis. Okay, so that way we know how orbitals are overlapping. They can be overlapping as sigma bond. They can be overlapping as a pi bond. Okay. Okay. So let's see here. So we have examples here. Okay, single bonds are always sigma bond. Okay, whenever you have a single bond, that means the connection is the maybe hydrogen. Hydrogen has a one sigma bond. Hydrogen can be formed with s orbital. So one s orbital of hydrogen is overlapping with another s orbital of hydrogen. Okay, so let me put the color here. So this is a sigma bond right here. It's a sigma bond, okay? It is overlapping of end to end of the s orbital, okay? Uh, one hydrogen of s orbital with the other hydrogen of s orbital, they don't have any other option. So they can overlapping end to end and they form a sigma bond. That is, single bonds are always sigma bonds. Please take attention to it. Single bonds are always a sigma bond. They don't have any other choice. They can create only one overlapping. Okay, because the pi overlap is greater, resulting in a stronger bond are more energies lowering. Okay, when we have a double bond a double bond will always have a single bond plus one pi bond. Okay, so if you have a double bond, there is one single bond there, and the others would have uh, overlapping either above the internuclear axis or below the internuclear axis. Okay, a triple bond, there is always one triple bond has three bonds, so one of them always will be single bond, plus you'll have two pi bonds. So if you have three bond, this guy will be a sigma bond, the other two will be a pi bonds. So you have two pi bonds, one will be above the internuclear axis, okay, and the other will be below the internuclear axis. I drew the picture earlier in the previous slides, below the internuclear axis. Okay, that's how bonds are created. Overlapping of orbitals can be created. You have option of single bond. You have option of for double bond. You have one sigma and one pi bond. For triple bond, you have one sigma and two pi bonds. So pretty much here, we need to know that we need to know the fact that here one thing they have in common that regardless of the number of bonds you have, whether it's a single bond or double bond, okay, or triple bond, okay, triple bond, they do have one commonality that every bond at least have one sigma bond. The sigma bond is common. The sigma bond. The sigma bond is the strongest one. Like I told you, the sigma bond is the ones that formed by the overlapping of the internuclear axis, end to end, like this. Okay. The others are options. The double bond may have one overlapping on the central axis, and then the other will be one on the top, one on the other. Is that it can be on the top of the internuclear axis or below the internuclear axis. Okay, so these are the two main overlapping of orbitals. Okay, I don't know what's going on here. Okay, so let me move on here. All right. Now the last one, which I would like to discuss in chapter 9, and then I can start with some practice problems with molecular orbital theory. Okay, this thing has to go. Okay, with molecular orbital theory. Now we have valence bond theory. We have valence. I want you to know the difference first before I continue. What is valence bond theory is focusing on, and what is molecular bond theory is focusing on. That's what we need to identify here. There's a big differences between a valence bond theory and a molecular or orbital bond theory. The valence bond theory is focusing with the individual atoms, the way how individual atoms are connected. That's called the valence bond theory. Whereas the molecular orbital theory is focusing with the entire molecule, okay, with the entire molecule, not with the individual atoms, but with the entire molecules. That we need to know. Before I go further, we need to know the difference between valence bond theory versus molecular orbital theory. They have differences, so we have to identify what's the difference. What's the difference between? What's the difference of the two? So I'm going to start with the molecule of hydrogen. Okay, H itself is an atom. All right, but I say when I H2 is a molecule. We have to we have to know the difference between H as a single atom. It's an atom. H2 is a molecule. So we wanted to investigate or explore H2 as a molecule. Okay, H2 as a molecule. Uh, the bond theory of as a molecule can be very much explained with the molecular orbital theory because it's a molecule, it's not an atom. Okay, remember the valence bond theory was focusing with atoms, with individual atoms, with with chlorine with chlorine, or hydrogen with hydrogen, with atoms, the way how atoms are connected. That's the valence bond theory. But the molecular orbital theory is focusing on the entire molecules, the entire molecule. So that's how the explanation starts. The explanation starts whether this is a molecular orbital theory or whether this is a valence bond theory. So in molecular orbital theory, we invoke that there is a wave nature of electrons. Electrons have something called a wave nature. So the wave nature of electrons, waves can be interact constructively. Constructively, the resulting orbital is lower in energy, and a bonding molecular orbital can be formed. So let's start. See, whenever two atomic orbitals combined, there are two kinds of combination. I would say a constructive combination and a destructive combination. All right, a constructive combination. I want you to take here constructive and destructive, or in other words, a negative type of combination and a positive type of combination. Destructive is a negative type. Where does that idea come from? Because the molecular orbital theory explains that electrons are like wave, the wave nature. Okay, so there is a bonding attraction of electrons, and there is anti-bonding. The two things simultaneously happens. You don't expect always that when two atomic orbitals combined, they always have a constructive a constructive type of combination. They also have a destructive type of combination. Okay, so we can start this example by explaining the with a simple diatomic molecule with hydrogen. Okay, so when hydrogen combined, you will have hydrogen has s orbital, one s combined with another one s. We are talking about two hydrogen atoms, right? So we have one hydrogen, hydrogen 1 and hydrogen 2. Actually, the two hydrogen combined, we get H2 molecule. When I write this way, it's very simple. Okay, two hydrogen combines, you get hydrogen as a molecule. But how did this happen? How did this happen? The way that when the two combines, now we're not talking about in 101 we just said that hydrogen has one electron, and then that one electron combined with another hydrogen with another electron, and the two electrons can form a single bond. This is one, this is another one. The two electrons can form a single bond because a pair of electrons, and it forms H2. Okay, um, this is okay, right? But according to the molecular orbital theory, we have to explore it farther than that. Okay, the combination it leads us the two atomic orbitals will lead us two types of combination. The two, the two atomic orbitals lead us to type of combination, which is a constructive type of combination um, that when we use constructive type of combination, which actually that a combination leads us a bonding of hydrogen molecular orbital with the lower energy. You can see that the energy goes from the bonding to anti-bonding as we go up. The energy increases with we have a lower energy here. This is lower energy, this is higher energy. Okay, this has a reason. Okay, uh, a lower energy creates a stable combination. A lower energy creates a stable combination. Please take a note on that. Lower energy is a stability, and that's going to be a constructive one. But the wave would also create another energy. So you see that there's like um, a concentrated electron density between the nuclei, a stable connection here, which is a sigma 1s between the nuclei. Looks like it is connected with the internuclear axis, which is sigma 1s. Sigma 1s, that is internuclear axis, and which I would say is stable. When the energy is getting higher, you can see a nodal plane between the nuclei. Okay, there's no connection here between the two hydrogen atom. Okay, this is the constructive one. There is anti-bonding here between the two. There is anti-bonding here, which leaves you with a destructive combination. By the way, this is not, I'm not talking about for hydrogen molecule. It can be for chlorine and chlorine. It can be for helium and helium. It can be for nitrogen and nitrogen, you name it, okay? Whenever two atoms combine as a molecule, you always have to expect, according to the molecular orbital theory, you always have to expect constructive and destructive combination. Okay, this is the general scheme, general picture because hydrogen is simple, because hydrogen doesn't have too much electrons, so hydrogen can be a good explanation for that. The others will be very complicated because they might move to s and p orbitals. Okay, but as the whole idea of the molecular orbital theory is explaining that you always expect with a constructive and a destructive combination. Constructive always creates at the lower energy level. Destructive always creates at higher energy level. So you will have a bonding and anti-bonding. Bonding and anti-bonding. So, um, okay, this is what we are discussing. So this is a continuation. Slide number 52 is a continuation about what I was discussing, I guess. If waves interact destructively, they are talking about this area here. Uh, if waves interact destructively, which is this area, the resulting orbital is higher in energy. Like I told you, the energy goes up here. And it's called the anti-bonding molecular orbital, the anti-bonding molecular orbital. By the way, we use asterisk here. We have sigma versus sigma with asterisk here. Okay, the sigma sign is a sign of bonding. The sigma with asterisk is a sign of anti-bonding. Okay, bonding versus anti-bonding. You always have the two situation. I think it's very small. I'm sure that you downloaded on your devices, on your computer or on your laptop. I'm pretty much sure you might have seen this very well. Always when molecules are overlapping, the orbitals are overlapping, you can see the two bonds here. So the anti-bonding orbitals are always generated from the higher energy. So as the energy increases, so that is instability here. Instability here, it's unstable. But here at lower energy, you will have a stable one, which is a sigma 1 S is here. And here you have maybe a sigma 1s with asterisk. Okay, with the anti-bonding there is no overlapping here. You can see the dots here. It's a nodal plane between the nuclei. Okay, so that's how when I say bonding and anti-bonding, don't get confused that this explains with a molecular orbital theory. A molecular orbital theory, unlike with the valence bond theory, valence bond theory is focusing with the individual atoms, whereas molecular orbital theory focusing with the molecules. Again, valence bond theory, valence bond theory considered just overlapping of electrons. I'm sorry, overlapping of orbitals. However, molecular orbital theory considers electrons as a wave. That's very important here. It's a wave. Okay, you can see the different meanings of waves. There is a stable wave, there is unstable wave. Okay, so the wave will be constructive wave. Okay, and the wave can be destructive wave at the same time. So that explanation comes from the molecular orbital theory. And then more importantly here, that we're focusing with molecules and we're focusing with the individual atoms. That's also another thing that we need to know between the two theories, with the valence bond theory and the molecular orbital theory. Even though they have commonality though, they have commonality. What is the common thing both of them have? The common thing both of them have is they both agree that it is overlapping of orbitals. It is overlapping of orbitals that is responsible for forming bonds. Okay, whether single bond, a double bond, triple bond, you name it. That's the commonality both of them have. Molecular orbital and valence bond theory, they do have that commonality. One is focusing with the individual atoms, which is valence bond theory. The other is focusing with the molecules, the entire molecules. Okay, So that's I wanted to highlight this. I wanted to highlight this, the difference between the two. Okay, let me move on here. That this is also can be, the we can we can draw the diagram that explains with the molecules of the hydrogen atom, so that to make it easier, okay? One hydrogen atom combined is one hydrogen atom. When they combine at the lower energy level, they provided us the two electrons here. One comes from here, the other comes from here. That's going to be a sigma 1s2. The electron configuration here is sigma 1s2, and it is a stable molecule. Now, the anti-bonding region here, which is the higher energy level, doesn't have any electrons here because all the electrons are already assigned in the lower energy level. So this part, the anti-bonding region, is vacant. The MO, by the way, refers to molecular orbital theory. Okay, so the word MO is molecular orbital theory. Okay, to make it, I would say VB. Okay, VB means that a valence bond theory. Okay, in most cases when we talk about VB and MO. MO, molecular orbital. VB refers to valence bond theory. So when we're talking about here, we have hydrogen. In hydrogen, the two electrons go into the bonding molecular orbital theory right here. The bond order is the one half the difference between the number of bonding and anti-bonding electrons. So now we have a bonding order. What is a bond order? A bond order is some kind of linear equation we can able to write. It's one half of the difference between the number of bonding, okay, the number of bonding minus the anti-bonding. The bond order. The bond order is very significant here. Bond order is half of the bonding and the anti-bonding. So in this case, we have the number of bonding we have here, okay, is to calculate the bond order. The bond order can be 1, the bond order can be 0, the bond order can be 2, the bond order can be 3, even the bond order can be a fraction. Okay, the bond order can be 1 over 2. The bond order can be 0.5. The bond order can be 2. The bond order can be 3. The bond order can be 0. If the bond order is 0, that means the two atoms, the molecule is not form a bond. Okay, if the bond order has a number, one over 2 is a number, or I mean, 1 over 2 is the same as 0.5. Anyway, I can change it 0.3. If there is a number, if there is always a number, it doesn't matter what number that you get after calculation. If there is a number, there is always, it is a sign, it's an indication that there is a bond. All right, an indication that there is a bond. What kind of bond? It's okay. You can generalize. You can generalize. Like 2 is a double bond. 3 is a triple bond. But if you ask me 1 over 2, I can only say yes, there is a bond. But if you ask me what kind of bond, my answer would be I don't know. I don't know. I cannot explain that. But and because there is a number, the two molecules form a bond. It's between non-bonding and a bonding. Maybe you may have 2.5. A bond order can be 2.5 after the calculation that we did here. So if you ask me, is this double bond or is it triple bond? In between. In between, it looks like there is a bond. There is a bond. That's important. There is a bond because if there is a number, whatever number that you get after the calculation, it means that there is a bond. That's important. We were not worried. We're not worried. If you get an integer, if you get 2 or 3 or 1, that's great. I mean, you can able to say 1 is a single bond, 2 is a double bond, 3 is a triple bond. All right. If you get a fraction or a decimal number, you just can say yes, yes, professor, it creates a bond, but don't worry about whether it is triple bond or double bond or single bond. It's not an issue here. So let's do the calculation here for hydrogen, okay? So the bond order, like I said, is half of it. It's the definition is right here, by the way, okay? You can read it later on. The bond order is the difference, is one half the difference between the number of bonding and the anti-bonding electrons. So we basically can calculate the bonding order of the hydrogen molecule. 1 over 2, the number of bonding, which is this guy here, is 2. The anti-bonding, which is this guy here, is 0. That means 1 over 2 times 2. 1 over 2 times 2 is 1. What does that mean? So that means the hydrogen molecules forms a single bond. One is a single bond, right? So what type of bond is that? That's sigma 1s. Okay, sigma 1s. So the electronic configuration, we cannot say just 1s2. Okay, we did that in 101. Okay, 1s2. But now we're going to make a little bit, we're going to explore this a little bit more. We just say one, I'm sorry, sigma 1s2. Sigma because the overlapping of the molecule is head to head. Okay, it's a sigma molecule, it's a sigma 1s2. So we can able to say this way. So bond order can help us to determine whether the molecules can form a bond or not. Even it can tell us not only formation of bond, it can tell us whether they can form a single bond or a double bond or a triple bond at the same time. Okay. Um, we may do some more example, pretty much sure. And here is an explanation, by the way, for hydrogen with 2 electrons, the bonding molecular orbital and none in the anti-bonding. They're talking about here. The bond order will be 1, and that means a single bond. Does hydrogen form a single bond? Of course, hydrogen forms a single bond. It's like this. Okay. If it was oxygen, oxygen forms a double bond. Okay, so what do you think is the bond order of oxygen? The bond order of oxygen, if I do a calculation according to the molecular orbital theory, should gives me 2, because it forms 2 bond. The bond order of nitrogen usually forms a triple bond. So the bond order of nitrogen basically would be 3. The bond order of oxygen would be 2. The bond order of hydrogen is 1. That's how bond order can be calculated. Okay. That's how bond order will be calculated. Okay, hold on. Let me see here. Where does this go? Okay, all right. Now I'm coming back here. Okay, yes, I got it right. Okay. Okay, this is a very interesting example. Let me, come on. What do I, is this not going? Come on. Let me try this. Okay, let me. Okay, looks like there's some technical issue here because okay, I'm just using the left side here. Now, how many of you have a predictable? Just wondering, how many of you have a predictable right now as we speak? Can you show me? I have 15 students in the class. How many of you have a predictable? Don't ask Shani. Thank you very much. I see Shani. I see Malachi. Thank you. I see Malachi's Hawkins, Jason Hawkins, I believe. Ellen
That
Hannah.
is correct.
Okay, thank you. Please try to have a predictable. It helps you a lot. It helps you. You can help me too. We are helping each other. Okay, you want to be successful in this course, so you want to get a good grade. So you need to have a predictable. I always say that, and I'm always nagging you to have a predictable because I want you to be successful in the course. I want you to understand the concept. So those of you, Malachi or Shane or Jason Hawkins, or some of you can tell me, we are investigating here to find out helium, okay? Where do you think helium would be found? You have a predict table. You don't have to worry. You just can tell me from the predict table and tell me a little bit about that element. Where is helium? Helium, He, okay.
Helium is above the noble gases.
Say one more time.
I said helium is above the noble gases.
Thank you. Thank you. Helium is noble gases, Shani. I really appreciate your participation. Helium is a noble gas. Helium is in group 8. Okay. Now, when we studied in 101, you remember that helium, all noble gases all noble gases, they are monoatomic. All right. Monoatomic, like helium, neon, okay, argon, xenon, krypton, I believe. Okay, all these are single atoms. Okay, they do not form a molecule. Like they do not form like they don't have O2 or N2 or Cl2. They don't form a molecule. These are molecules. Okay. One other characteristic that helium or all noble gases they have, they are inert. Their outermost shell is already filled, completely filled. They are inert. They don't need to form a combination with other elements. That is, we discussed uh, we discussed the fact that they don't need to form a molecule, but we have to prove that with a molecular orbital theory. Molecular orbital theory is a proof for us. You know, theoretically, we know that helium doesn't form a molecule, but practically, we can see that what is the reason that helium doesn't form as a molecule like oxygen, like He2? Why? What's the reason? Okay, so we let's make an investigation. You see, if you have a predict table, helium carries 2 electrons. So we have another helium, which also carry 2 electrons. So altogether we have 4 electrons. You can see one of the helium atom here has 2 electrons. I would say helium 1 here. You have another helium, which is helium 2 here, right? So what's happening here that each orbitals always hold this 2 electron, that the maximum number of electrons they can hold. So one electron goes from here, the other electrons goes from here. So at the lower energy level, you will have a sigma 1s2, a sigma 1s2, okay? Now, the 2 electrons formed here in the anti-bonding region, which is a sigma 1s2 with asterisk sign, okay? All right. So all the electrons are assigned 2 electrons in the lower energy level, 2 electrons at the higher energy level, which is the anti-bonding region. Okay. Now we wanted to know that if there is a bond order for helium molecule. Okay. A bond order is the difference between half of the bonding electrons minus the anti-bonding electrons. That's how a bond order can be calculated. Bonding minus anti-bonding. Actually, the definition of bond order is there. So when you do the calculation, the bonding electrons, which is the stable one, is 2. Okay, I cannot write here. Hold on, let me see. 1/2 minus the anti-bonding is also has a 2 electron. So we do have 1/2 1/2 times 0, right? 1/2 times 0. 1/2 times 0 is gives you what? 0, right? Any number multiplied by 0 gives you 0, right? Obviously. So that means helium as a molecule doesn't exist. Helium as a molecule does not exist, which we prove on the bond order. Okay? If it was as helium as an atom, yes. So all noble, it's not about helium, by the way. All noble gases will not be existed or will not be existed as a diatomic molecule. That explanation come from the molecular orbital theory. Molecular orbital theory gives you a justification. Actually, we get a justification here. It's a justification that whether we get whether we molecule can be existed as a diatomic molecule or cannot be existed as single atom. Okay, so molecular orbital theory can explain that very well. Maybe the okay, next one here. Now, remember that the molecular orbital theory is not about only the s orbital. Okay, here is the picture that atomic orbital, one atomic orbital, one combined with another atomic orbital, you get a bonding molecular orbital and anti-bonding molecular orbital. But now we're going to see the fact that how about p orbitals, okay? Earlier we were talking about s orbital. So p has three different orientation. We have px, we have py, we have pz, right? So we have, for example, here a two pz orbitals, okay? They are overlapping head to head. If they are overlapping head to head, then that's going to be the internuclear axis. They are overlapping head to head in the internuclear axis, then you will get a sigma, which is the strongest one. For two atoms with both s and p orbitals, there are two types of interaction. The s and the p orbitals, they face each other, they overlap in a sigma fashion. Okay, they here they are explaining a little bit different. They are talking about if you have s orbital with p orbital like this, because this is s, this is p. Okay, okay, so maybe I can use a different color here. Okay, actually the explanation here is like this guy here. Okay, the s and the p orbitals, they face each other in the sigma fashion. Okay, the other two sets of p orbitals overlap in a pi fashion. So this one here, if you have two orbitals, for example, you have a px and a px, two orbitals combined, you may have a pi 2p, which is one is with a lower energy level, which is a pi 2p, but because the combination here is not the internuclear axis, not in the middle, but the combination would be here, either can be on the top or either can be on the bottom. Remember that earlier we were talking about a sigma combination and a pi combination. Okay, so this is a combination of the pi 2p, which is a stable one, a pi 2p with the unstable one. Okay, so you have the situation. You may have a situation with a py, two py can be combined. You will have a different types of orientation. But again, this is a pi 2p and a pi 2p with the asterisk, because like always, when two atomic orbitals are combined, you have a lower energy here. A lower energy is associated with stable. So that's going to be a pi 2p, okay, which is a stable one. It is pi because the connection is not on the head to head, but the connection is either above the internuclear axis or below the internuclear axis, but it's a connection. It's a stable connection. The unstable one, the destructive one, is right here. There is a nodal plane, which is sigma 2p with the asterisk sign here. Okay, so we have the options of connection in molecular orbital theory It's not about only with the s, it goes with the p as well. P orbitals will also have the same situation, that they can create a pi to p on the anti-pi to p. Okay, so like you can have the resulting molecular orbital theories. You can have a sigma and a pi bonding molecular orbitals. This is a combination of, if you have S and P, okay, S and P orbitals. So you will have this kind of geometry, this kind of arrangement. So we can able to do this calculation to determine if they contain S and P. We can have the sigma bond and we can have a bibonding molecular orbitals, and at the same time you will have the anti-bonding of sigma and the anti-bonding of pi here. You see, you have a sigma to S constructive combination, you have a destructive combination. If you have here, if the overlapping is head to head, you have a sigma 2p. If you have a sigma 2p, you need to expect that you have the anti-bonding region on the top. It's sigma 2p with asterisk. You have a pi 2p, this can be py or pz, which is the head, not head, it's above the internuclear axis or below the internuclear axis, and you will have a pi 2p, the asterisk one. Remember that this is, p has three different orbitals, okay? So these three different orbitals have three different orientation. They do have a sigma, they do have a pi, okay? So that's the orientation that they have here. Just like the S have a sigma to S and anti-sigma to S at the same time. This is the way how the distributions of the electrons. Maybe we can able to see something here. What we see here, basically, I don't know why this not gone here. Let me see if I can able to share it one more time so that I can able to. Where is it at? Okay, it's right here. All right, okay. So just look for the consideration here, the pictures here, that let's consider with boron here, right? When you talk about boron, you have a sigma 2s. Boron is, you can, how, Shani or Hawking or Malakai, you guys have predictable. Boron is in group 3, I believe, right? I don't have predictable myself, but it might
It is.
be in group 3, right? Okay, so that means boron has, oh, hold on. Right, so boron has 3 electrons, right? The other boron has 3 electrons, and we are trying to see that the bond order, or as a molecule, boron as a molecule, because the MO is molecules, it's a molecular orbital theory. So we're talking about as a molecule here. So we can see that sigma 2s holds 2 electrons. Okay, we have altogether 6 electrons, right? We are trying to address all these 6 electrons. The first 2 electron will be on the sigma 2s. The second 2 electrons will be on the anti-sigma 2s. And then the 2 electrons are left here. So they have to go to the pi 2p, okay? Each of them, this is called the electrons have to be filled with the vacant orbitals they have. So even if you have 2 electrons, each of them should get, because they have the same energy level. Since they have the same energy level, each of them should get 1 electrons each. Okay. Now, when we talk about the bond order, okay, the bond order here is going to be for boron. I'm talking about for boron. Maybe I can use a different color here. The bond order for B, which is boron, half of the bonding electrons, okay, half of the bonding electrons. So the bonding electrons we have here is 2, and we also have here 2, okay, one from the 1p and the other from the other p. We have 2 and 2, we have 4, the bonding pair of electrons. The anti-bonding electrons, we have 2, okay. So we definitely have when we do the calculation, it's going to be 1/2 divided by 2 is going to be 1. So that's why you see here it's 1. That's how they calculate 1. So the bonding order, the bond enthalpy in kilojoules per mole, actually, this is something that's given to you is 290, but I'm going to explain a little bit about why these numbers are varied, okay? So it's 290 here. The bond length is measured in angstroms. Angstroms, remember that I told you angstroms the other day. Angstroms is the unit that's measured the dimension or the size of atoms. And 1 angstrom is actually equals to 10 to the power of minus 10 meter, if I don't make a mistake. Okay, it's a very small number. So the bond length is 1.59, and the magnetic behavior is a paramagnetic nature. It has a paramagnetic nature. Okay, so that means it has a magnetic character. The magnetic character actually comes from the undistributed number of electrons. That's very important. Here, for example, it's a diamagnetic because all of them are pair. There is unpaired number of, the more unpaired, let me write this down, this is very important. The more unpaired electrons will result to a paramagnetic. Okay, if you have a pair number of electrons, that is going to be diamagnetic. Now you cannot tell an element whether it is or you cannot tell a molecule. Sorry, so saying for element, we are not talking about element, we are talking about molecules. You cannot predict a molecule just by saying or just by looking up, unless you know the molecular orbital theory. The molecular orbital theory would also verify that whether the molecule is diamagnetic or paramagnetic. That's very important here. So you can see here, for example, the bond order for, we're talking about carbon. Okay, carbon, I know that carbon is in group 4. So the molecule of carbon, altogether they have 8. Okay, if it's carbon 2, it's going to be 8 electrons, right? So how do we arrange those 8 electrons? If you look here, the lower energy level sigma will take 2, the anti-sigma will take another 2, and we have from S, we go to P. The P orbitals will take 2 each. So that 2, 4, 6, 8. All the 8 electrons is gone. So from that, we can able to calculate the bond order. The bond order, again, is half of the bonding electrons. The bonding electrons are 2 here. Another 2 is here. Another 2 is here. So 6. The bonding electrons are 6. The anti-bonding electron is 2, which is right here. 6 minus 2. So that gives us 4. That gives us 2, which means the bond order is 2 right here. And remember that the bond enthalpy is 620 and the bond length is 1.31. And it has a diamagnetic nature. So I can, because we don't have time now, it's 10:44, I have to take attendance. I want to compare, I'm going to continue on Friday. This is the last portion and I'm going to continue on that and we're going to start reviews. Here, the two can tell me a lot. You see, what I want you to relate is as the number of bond order is less, the bond length is longer because the bond order is single bond versus double bond. Double bond is tighter, very tight. So that means they are short in distance. You see, 1.59 for a single bond, 1.31 for a double bond. You see, and in terms of energy, bond enthalpy is energy, as we discussed in chapter 8. Enthalpy is the energy that's required, how much energy is required to break the bond. For a single bond is 290, a small number. For a double bond is 620, it's almost twice or three times because that's a double bond. So this is single bond, whereas this is a double bond. So it's obvious that the energy increases. And notice here that because it's double bond, the carbon atoms or the carbon molecules are close to each other. If the carbon molecules, if the carbon molecules are close to each other, that means it takes a larger energy to break up the bond, which is 620. And it's a diamagnetic. A diamagnetic because there is no single pair here. If you look up here, double, 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 double. Here you have a single unpaired number of electrons. I already wrote a note here. I hope you took this note. The more unpaired electrons that you have, it's a paramagnetic. If all of pair number of electrons, if all are pair number of electrons, then it is diamagnetic. So this is a good scenario between boron and carbon. Boron and carbon. See, so I'm going to wrap up this lecture here today. I'll do my best to upload this video and then post that to you. For a quick, I will take attendance. Now, I also wanted to know, please, I would like to know if you are in a PTech program, one way or the other way, please send it to me because I need to send a report. If you can text me if you want to, you can use Viber or WhatsApp. Just use 410-292-2110. Text me or send me an email. Send me an email. I'll look at the email too, okay? So that I know who is who. I took a note the other day. I'm sorry, I lost that paper. So please text me that, or you can just tell me now when I call your name. Oh, I'm on PTech. I'll take a note. That's easy. Okay, either way. So let me go ahead and take the attendance before if there is any disconnection. I'm glad that we don't have any disconnection today. Class goes smoothly. Very good. Connection is not bad. Okay, so let me go here, take a quick attendance. Okay, we have, please say yes, I'm here, or text me a text message. If you don't do that, I'm considering that you're not in the room, okay? Either way, text me if you cannot, if you have issues with the mic, or say yes, okay? But when I call your name, okay? Maybe I'm just trying to open now. Come on, it's opening, it's opening. Okay, Ifoma Agonar, Ifoma, are you there?
Present.
Thank you. Oti Agonar.
Present.
Thank you. Udo Agonar.
Present.
Thank you. Muhammad Alijami.
Yes, I'm here.
Okay, thank you. Malakai Bunch.
Here.
Thank you. Caleb Davis.
Here.
Thank you. Shane.
Here.
Okay. Marvelous. Go to Marvelous.
Yeah.
Okay, thank you. Jason Hawkins.
Here.
Thank you. Ellen Honor. Ellen.
I'm here.
Thank you. Noreen Nuru.
I'm here.
Thank you. Zikia Reni.
Here.
Thank you. Raina Revel. Okay, Raina, you're not here. I didn't see any text message as well. If anybody see text message, let me know. So just for review, I have everybody here except Raina Rebel. So I need from you to send me that you are in a PTEC session, and then I'm going to take a note on that. Other than that, I'll send you the review guideline for this week. For Friday, we're going to start review, and we plan to have our first exam next week. And I'll tell you the procedure how we take a chapter-based exam on Friday. I thank you very much, everybody, for your patience. I'll see you on Friday. Okay?
Thank you.
Uh,
Friday.
Doctor,
Thank you very much.
Doctor,
Yeah. Yes. Yes.
I have a question if you have a minute.
Okay. Okay. Muhammad. Okay. Go ahead. Yes.
Yeah, finally they are back my schedule.
Okay.
And,
Okay. I saw.
yeah.
I saw your name back now.
Yeah, thank you for that. I'm already talked to my lab professor, and he gave me an excuse to do the what I missed.
Okay, for
Mm,
chapter 8 quiz and chapter
yeah.
8 assignment, I'm going to give you an extension till this Friday midnight, okay?
Okay, thank you for that.
To let you
And I think there is a problem in the Canvas because everything the due date like February, and we are in June. I'm sorry, we are in July. Because the everything, the assignment, the quizzes,
no,
the
don't worry
due.
about that. I'll extend that. I'll give you an extension for that. So I'm going to, you can see that an extension, but you also, Mohammed, you also need to purchase the access code to do the assignment. Do you have the
I'm already paid for the access code.
Okay, okay.
Yeah.
So okay. If you have the access code, I don't think you'll have a problem. But like I say, I will because you're not reinstated. I will give you an extension for the quiz and the assignment till this
Which quiz is quiz 8 and
chapter 8. Yes, quiz 8 is from chapter 8, and the assignment is from chapter 8 at the same time.
the assignment? Okay, thank you.
All right.
I'm trying to do it by Friday.
Yes, you have to do it before the due date. Okay. That's
Okay,
simple. Okay.
thank you.
I have a question.
All right, Mohammed. Yes,
Have a good day.
Jason.
Sorry, from the exam for 101, I was confused on one. It said physical change by process, which matter changes from one physical state to another. And that's technically true, but not all physical changes are state changes. So I was kind of confused on like which way that question was leaning.
A physical change is a change of shape, a change of size, a change of state from solid to liquid, from liquid to gas, or vice versa. That's a physical change.
Yeah, so
Mhm.
the question stated that physical change is a state change. So that technically be false because that doesn't include everything, right?
No. Why? A physical change, a change of state. A change of state. State means you have three states of matter, which means solid to liquid, liquid to gas.
Yeah, I get that, but the question worded it like it was talking that physical change is just a state change. You get what I'm saying?
Okay, I'm going to look the English word, but Jason, I'm looking for the chemistry perspective. From the chemistry point of view, a physical change is a change of status. That means change of solid to liquid, liquid to gas. I don't know how it was written. I have to look on that.
That's fine. I just wanted to ask because the wording confused me a little bit. Is all.
Okay. Did you wait a minute? You took the exam today?
Yeah, yeah.
What 9 a.m.?
Yeah, I mean, I didn't want to get marked for attendance. So I had my phone off to the side, not actually
Wow.
fully paying attention because.
So you're in the class at the same time, and then you're taking the exam.
Yeah, I talked to you about that in the beginning. I told you I was in both classes.
That's not a problem, Jason. I'm just admiring you that how do you able to make the two that you have a lecture and you take the exam? It's not that. I mean, if you'd have to ask me, I can change that like for 6 p.m. because a lot of them is taking 6 p.m. I'll take a note. But if you taken both at the same time, I mean it's great. I mean, you are a multitask person. That's all I can say.
I appreciate that.
All right. Okay. I'll see how are the exam in general, by the way?
I did okay. I got an 86. It's not terrible.
Okay. All right. Okay. All right. I'm going. We will have. I think we will have review classes with you guys from six. I mean, from 11 to 12. So I may have to go. I may have to create another slide. So I have only 5 minutes left. I'll see you.
That's fine. Thank you for answering my question.
Okay. You no problem, Jason.
Have a good one.
Okay. Bye.